This is Independent Lesson 3.4. We're going to be looking at an introduction into experimental design. So there's a lot of vocabulary for this lesson, and it's just because there are a lot of little things that we want to very clearly categorize and clarify for experimental design. So first off, we talked about this in an earlier lesson, experimental units. So these are the actual things or people that are assigned treatments. And within those, if the units are human, that means we are calling them subjects. We also have the explanatory variable. We might recognize this from the linear regression unit, but here this is just a variable whose levels are manipulated intentionally, aka this is going to be our independent variable. And another way we can describe explanatory variables are factors. So this is usually just when there's more than one variable being manipulated, and we can also think of factors as a type or category of treatments. And treatments are those levels or combinations of levels of the explanatory variable. So when we talk about treatments, a lot of the questions ask you to define what those treatments are. And the treatments are just the actual thing that's going to be imposed on the units or subjects if we're dealing with humans. We have our response variable, so this is the outcome that's going to be measured after the treatment has been imposed. And then we have the confounding variables. So the definition here says it's a variable related to explanatory and influences the response, causing a misconception. Now that's a lot of stuff, but basically, in regular English, we're talking about a variable that confuses us, the people designing the study, and usually with confounding variables, that means we don't know which variable is causing the response. And in some cases, it can actually be a combination of variables. And now we get into blinding. So single blinding is either the subjects or the person recording the response do not know which treatment was imposed, which is great for generalizing about populations and establishing cause and effect relationships. But what we really want is this double blind experiment where neither the subject nor the person recording the response know which one. So if I was doing an experiment, I wouldn't know which treatment I was giving you guys, and you wouldn't know which one you were receiving. Only an outside third party would know this. A big part of experiments is having a control group, so just something that is not given a treatment or given a placebo, and a placebo is that inactive substance made to look exactly like a treatment, aka the sugar pill treatment is what I like to call it, especially since most experiments that we're going to be seeing and descriptions of experiments have to do with drug tests and things like that, and really placebos are those sugar pills, things that the subjects think are the actual drug, but in reality it's not really a treatment, which then causes the placebo effect. So that is what happens when they have a response. So they think the drug is working when it's just their brain telling them that it has to be because it is a drug, when in reality it is not. What we're really going for in the end is the next two things. So statistical inference, so drawing those conclusions based on the data we have collected, and seeing whether our results are statistically significant, meaning they are so extreme by chance alone that chance cannot explain the outcome. We also have blocking, so this is groups that are of similar characteristics with respect to the variable you are blocking for. Good example of blocking is blocking by grade level, blocking by birth sex. These people or subjects within the experiment share these characteristics. And I know it says replication, but a good experiment always has more than one unit, so that way we can make sure our results are as valid as possible. And of course, we want things to be random. It ensures as least bias as possible. Now, there are 4 components to a well-designed experiment. First, we want to have comparison. So we want to have 2 or more treatments. And that's the key there. And the reason why we do this is so that way we can help prevent confounding. And really, that control group provides that baseline for comparison. The second thing we want is random assignment, which we are using chance process to assign experimental units to treatments. Reason why we do that is to help ensure the effects of other variables. So help ensure effects of other variables, and we want to make sure that they are spread evenly. There we go. It's not a very good A. We want to make sure they're spread evenly among the groups. The third principle we want is control. So we want to keep other variables that might affect the response the same for the other groups. And this is just to help reduce variability in the response. And the fourth is replication. So again, that idea of replication is just to use as many experimental units as possible in each group. This is all about helping to balance, balance out the effects of chance. So make sure that we are allowing, well, this also allows us to determine that the treatment itself is causing the response. And not just chance. Now let's look at a couple of examples. So example 1, I'm interested in seeing if traditional classroom produces higher test instruction. So we've seen this example before. I give 100 AP Stats students a pretest, and then I randomly divide them into 2 groups. One group goes through the course in a traditional classroom setting, and the other takes the course online, ironically enough. And at the end of the school year, I'm going to test all the students again and compare their scores. So first off, we want to identify the following. So the experimental units, these are the people receiving the treatment. And the people receiving the treatment here are the 100 AP Stats students that I have selected out. The explanatory variable, so the treatment itself, well, the category of treatment, and that independent variable is the type of instruction. The response that I'm looking for is to see whether the test scores are good or not, and then I'm going to compare them. So I'm looking to find that my response variable is the test scores at the end of the course. And my treatments, there were two different types of treatments that my students went through. Either they had the traditional classroom, or they took the course online. There was a virtual class. Example 2, students in my AP class are interested in how exercise affects heart rate. So there's some important information here. They want to know how exercise affects heart rate. Students first measured their resting heart rate. Then students did squats for 30 seconds, 60 seconds, and 90 seconds. So that's some more important information here. So they did squats, and they also squatted with no weights, 2-pound dumbbells and 5-pound dumbbells. And we also know that 36 students took part in the activity. 4 students participated in each combination of time and weights, and after they measured their heart rate. So again, the experimental units are just the people receiving the treatment. So these are the 36 students who participated. That explanatory variable, that independent thing we're looking at here, is exercise and time, with the squats and the amount of time they did them. That response variable, so the effect we're looking for, is the heart rate. And the treatments, here we actually have 9 treatments. And those 9 treatments listed out, well, they could either squat for 30 seconds, no weight. They could squat for 30 seconds with 2 pounds. 30 seconds, 5 pounds. 60 pounds, no weight. And getting all those combinations in until we get to the 90 seconds with 5 pounds. We have these different types of experimental design. We're just going over these completely randomized design. So this doesn't require that treatments be assigned to an equal number of units. The only requirement is that treatments are assigned to the groups using a random process. The randomized block design, which is one of the most common along with completely randomized. We first separate those units into groups based on some sort of characteristic, usually birth, sex, or age, or things like that. And then we randomly assign the units, treatments within each block separately. We do that to account for variation in the response, and we can determine if one treatment is actually more effective over the other. And last but not least, we have matched pair. So this is a common type of block design used when we want to compare 2 different treatments. So usually we match pairs of similar units. So usually, we could pair a woman of similar weight and age with another female of similar weight and age, so that way we could see how it affects similar people. Then we will randomly assign them to see which of the pair gets the first treatment, and that other one will get the second treatment. Often the pair in a matched pairs design is just going to be one, and then they will get one treatment after the other. That order will just still be randomized. We then have 4 steps to follow when designing an experiment. So first we need to determine which type is best. That's going to depend on the context and the scenario given to you. We're going to diagram our experiment first, and we're going to describe exactly how we're going to randomly assign the treatments and explain exactly what we're comparing once the data is gathered. There are 3 ways to randomly assign those units. So we can either draw labels without replacement, and they must be on equally sized slips of paper, random number generator, table of random digits, usually, really, this is the 3 different ways to take an SRS. So let's look at an example here. So we want to look at, does texting while driving cause accidents? We have 40 of my students that have volunteered for a study to determine if driving causes more accidents. Marin County Sheriff's Department has given us a driving simulator to use in the experiment, and we're going to design something that is completely randomized. So completely randomized experiment, we're going to start out with our individuals, our units. So we have the 40 volunteers. Since we're doing a completely randomized design, all that's left, we have those 40 volunteers. From here, we are doing the random assignment. In both places. So we're going to randomly assign 20 to one treatment and 20 to the other treatment. In this case, treatment 1 would be, we're actually going to, in the simulator, of course, we're going to have them drive while texting. And that other treatment should be, we're not driving while texting. Afterwards, we've imposed the treatments. After the treatments are done, we should take them back together. And there should be some sort of comparing. And in this case, since we're seeing if driving causing more accidents, it would make sense here to compare the average number of accidents for both groups. So if we were to write this out as a description, we'd start with the 40 volunteers, but we are splitting those 40 volunteers into 2 treatment groups. So we can use an RNG, a random number generator. And we will generate 20 unique numbers. For treatment 1. And the other 20 will go to treatment 2. And afterwards, we will do the comparison. So now it's brought to my attention that gender could be another contributing factor to the number of accidents people get into. Now we're looking at determining what design is a little bit more appropriate here. And here it's going to be a randomized block design, because now we're considering splitting them into two different categories. So splitting them into female and male. We will have random assignment in both spots. That's what the RA stands for, is random assignment. And remember, the treatment that we want is either drive with texting or drive without texting, and the same for the other group. And just like before, instead now we're comparing within the groups. We're going to compare that average number of accidents. And we're just going to put little quotes there. And we could write it out in words like we did for example 3. It's not really necessary. Doing this sort of tells me and the graders exactly what you're trying to do. So example 5, a student now brings up that each student has a different driving style with many other variables that can influence the number of accidents. What could we use to control this confounding variable within this? Well, since we're talking about each individual being different, this is going to mean we want a matched pair design. And in this case, it would be a matched pair where each volunteer receives both treatments. So let's say we have our volunteer, and I know I have a little stick figure here. They are going to be randomly assigned a treatment. So this can go both ways. So either they are driving with texting, or it goes the other way. They are driving without texting. And afterwards, at some sort of later time, they should receive whatever treatment is left, that remaining treatment. And after that, just like before, we want to compare that average number of accidents. So, let's say we've gathered data and completed our study. What can we then do with the information, and what conclusion can we come to? So there's two questions that we need to ask ourselves. Did we randomly sample? If yes, we can generalize. If no, we can't. Did we randomly assign treatments? If yes, we can establish cause and effect. If not, we can't establish cause and effect. So, for example 6, we're almost done. Does classical music or playing classical music increase test score? I want to study the effects of playing classical music while testing on my students. So first, I'm going to randomly assign 2 of my students or 2 of my classes to listen to music and 2 classes with no music while taking an exam. And on her students, the fact that I'm using my students is important. The students who listened to classical music had a test average of 80.2, and those who didn't had an average of 77.5. So, conclusions here. First, did we randomly sample? No, the fact that I used my students, I took a convenient sample, people that were easy for me to reach. So here we can't generalize. Our findings. And that's because, oops, there we go. The students were not randomly selected. But since we did randomly assign, this means we can establish cause and effect. And that was since the treatments were randomly assigned. Let's look at example 7. So, do female students at San Marin High spend more time studying than male students? So, AP Stats students, such as yourselves, randomly selected 100 male and 100 female students and asked them how many hours a night they study. Female students surveyed an average of 1.875 per night, and male students averaged 0.975 per night. What conclusions can we draw? So first, well, let's make sure we get this down. We just ask them how many hours a night they study, which is important, although it may not seem like it at first. Here, the individuals were randomly selected, so here we can generalize about the population. Which, in this case, is San Marin High School students, since they were randomly selected. But because they just asked them how many hours a night, nothing was really randomly assigned. This means we can't establish cause and effect. And this is because no treatments, and no treatments in general, but if we were to consider any of them treatments, the fact is they were not randomly assigned. This was independent lesson 3.4 on Intro to Experimental Design. Please let me know if you guys have any questions. Be sure to reach out and I'll answer what you got. Thanks, guys.